But is there anyone at the back who wants to hear me who can't? Well, since people are not afraid to talk, hopefully, I'm going to use my own voice. I'm also going to follow somebody who our guest of honor, namely Frank Chen-Ning Yang. I use his name in the United States, which is Frank. It's an honor for me to be here. He has known Mark Katz a long time, and one of the things I liked about Mark Katz, he said, well, you see I'm wearing a jacket. I'll come here in the light so that you can check I'm wearing the jacket. And now that you know I have one, I'm going to take it off. It's quite warm in Singapore, and put it on the side here. Now, I've put something up about my title, and my title is addressing the question about how theorists should think about the world outside. And although I was trained as a physicist and to some degree as a mathematician, I've also worked in chemistry and in biophysics at least. And in all of those questions, the question arises as to how, coming to it as a theorist, you should think about it. And so what you see before you on the left is what I would say, namely, the first thing you need to form is some idea of a picture of what's out there. What we've learned over the last half century is basically then that it's very important to try and actually calculate things. And since most things are very hard to calculate, even with the best computers now available, then you need some sort of workable model. And that workable model may still result in an awful lot of very hard mathematics. I'll touch on some of that. And beyond that, you know that your model is bound to be approximate. And the crucial thing is to understand the origin and the nature of the approximations. Then, and this is the basis of the sciences, and what distinguishes us from the ancient Greeks, who were pretty good philosophers and thought about a lot of these things, is the experimental method. One wants to see what actually happened in reality.
Is it possible to use the mic?
Well, the question is it possible to use the microphone? Well, I take it from the laughter that it's not necessary.
Okay, it's okay. And because it's not picking up your voice.
Okay, but if there are problems, I'm happy to use the microphone, but I don't think there will be. So one of the title you see addresses the understanding of the physical world, and there's a gap here that I'm going to point to. And give me a second while I remove the pointer from my pocket. So there's a gap here. And basically, my argument is that you can put whatever you like into that gap, and nevertheless, what I'm going to say is illustrative. Now, I'm going to put phase transitions and critical phenomena into that gap. I'll explain what they are as we go along. And the first question is, well, what about this picture on the right here? And one of the things you can't see, unfortunately, the things are of a large scale here, a little too far, the distance between the audience and the screen. One of the things you can't see is that the scale here is in degrees. This is the specific heat of liquid helium when it becomes a superfluid. So at the high temperature side, it's an ordinary fluid, and the low temperature side, it's a superfluid. It flows without any friction at all. If I multiply the scale in temperature by 1,000, this is the same picture. And as you can see, it's phenomenally sharp even on that scale. If I multiply by another 1,000, you can start to see maybe a little uncertainty in the data, but it's 1,000,000, 2,000 squared, 1,000 squared from here to here. What you can't see is, I can see it, there's a little red dot here and a little red dot there, And the answer is that the next door picture is that thing expanded out. Okay, so now one of the questions I'm going to ask is, what's this got to do with anything that we might want to concern ourselves about? So I'm going to talk about phase transitions. I'm going to talk about universality and singularity. And if I can pull this up, I'm going to say, well, how does that differ from stamp collecting and philately, which is the professional name for stamp collecting? Now, I'm certainly not against stamp collecting. One of the early awards I won was for stamp collecting. So I'm all in favor of it. But as soon as you start stamp collecting, you start thinking about the stamps, and that's going to be essentially the issue. So now I'd like to talk a little bit further about the scales here. So let's see if I can stay in phase with what I want. And so I'm going to show up here on this side some of the pictures that show you a little bit more about the, there we are, let's see if I can center it. There we are, that's centered. This shows you the scale again of the helium, and it shows it again on the microsecond. So this is already an enlargement of the scale on the left. And if I go to one more, and we'll see this further on in the statement, we'll see further information on that. Let me put here what happens if you just go from 1 microdegree. So this is the equivalent of the last one here, and it shows the beauty of the experiments, namely that it's still sharp on the microdegree, as you see here. So this is the question I'm going to address. What is the way in which we can think about this? And in particular then, what I'm going to show you next is a little game, a board game if you like. And the question is, what's this board game got to do with anything else? So let me show you the board game here. And let's see if I can get it more or less right so that it's there. I think that's about right. And so this is a domino board game, and so I've got the dominoes there, and the question is simply how many ways can you arrange these objects on the domino board? And there's a very simple way of answering that. If the board is small, you just have your shot and you try it and you see what works. And it's pretty clear that if it's a small board, and the smallest board you can have that'll fit a domino as a 2x2 board. And so let me indicate here that if I want one domino, that's it. And then I want to fill it up with dominoes, so there's the second one. And the only alternative is this. Okay, that's the only change. And so the number of ways of doing this here is 2. You might say, well, what are the alternatives? And the alternatives are not many more. When I come to look at the slightly bigger board, then there are more alternatives, and it's already, I've filled in the 4x4. Well, there's not many choices here, but I've filled it in. But you can sort of see that if I want to play this game and play it correctly, there's 36 alternatives. When it comes to a big board like this, you see there's not much choice at this stage. You have to put this domino in, otherwise there's going to be a gap there. But beyond that, I have some choice, and if I put this domino here, then I'm restricted in either putting them on that way or the other way. But as you see, so it's not a trivial game. And in point of fact, the number of ways of writing the dominoes in here is up in the 12 millions. I do have the actual number here, so let me fill it in. It's 12 million. And then one of the questions is going to be, well, this is just a pure mathematical question. What's the answer got to do with any of the physics questions that I was raising? And that's the question I want to basically address for you. So I'd like to put in this number in full, and that means I'd like to copy from my notes to get it right. 12 million, I told you, but then it becomes 988. And now you may say, well, what does this number matter? And the only thing that it matters is that the fact that I can show you that it's that number, and the fact that this is perhaps a square number, so this is actually 2 to the 4 times 901 squared. The only significance is that I can tell you exactly, tells you that I know how to handle this problem mathematically. And so I think if you aren't asking the question, so what, at this stage, then you're being very generous, because I think there's no obvious reason why this domino game should have anything to do with the superfluidity that I see here on the superfluid side and on the non-superfluid side. What connection could there possibly be between these? Well, let me advance a little further then and tell you the next way I would like to think about this. And so I'm going to leave this aside, and we'll come to it at some later stage. But I'd like to put up here, let's see if I can adjust it correctly. Now, you have to take account of the fact that they tell me there are 2 screens here, and thereby I've screwed everything up. Well, that merely goes to show that modern methods of projection are not always as perfect as they are. So what you see here is actually a container of carbon dioxide, so an everyday gas, what you breathe out when you breathe. And what you're seeing this is at a particular density, about 0.5 gram per cc, particular density. And on this side, it's separated into a liquid and a vapor, and there are here 3 spheres. Now, those spheres look a little peculiar. They don't look round on the screen. You just have to make allowance for that. They are round. Here, I come well above what is going to be the critical temperature. This was a phenomenon that was first observed many, many years ago. And as you see now, these 3 spheres are of slightly different density. And the one in the middle just floats in the middle at the right density. This is done in the gravitational field, so the liquid carbon dioxide is slightly denser here at the bottom than at the top. When I say this is liquid, this is neither liquid nor vapor, because one of the things you wondered was a discovery was that at the critical temperature, the difference between the liquid at the bottom here and the vapor at the top there just disappears. But en route to disappearing, you see some sort of flickering here, and that flickering is an indication of what's called critical opalescence. If you hold this up, then and look at a light behind it, then you'll see that the blue light is diffracted. And so what you see here, this is illuminated from the side. Essentially, you're seeing the blue light being refracted. Here, the whole interface is lost in essentially fog. And as you see, rising the temperature in this direction, by the time we get to here, there's no sign of the interface. So the critical phenomena is what is lost at the interface. Now, how should we describe that? Well, the way of describing that, and I'm going to show you, is an interesting experiment that you'll see, and it's important to understand it. Let me see if I can line that up for you. That's right. Now, what you can vaguely see is the shape of this. And if you look down at the bottom right-hand corner, you'll see that there's an indication of the density here. That says it's the density. So you're seeing the density across here, and you're seeing the temperature vertically. And the critical temperature is at the top here. So this temperature scale is normalized by the critical temperature, and the density scale is normalized by the critical density. This was a picture that was produced by Guggenheim sometime in the late 30s, and this is taken from his book. And the question then is, here he shows a series of different compounds. Well, here there's neon, argon, krypton, xenon. Here there comes oxygen. Here comes carbon monoxide, and so on, methane. And what he's illustrating to you here is that these all seem to obey the same sort of law. And then the question I'm going to address is, yes, but what's the shape of the curve when I get to the very top? And so the question we're going to be talking about is, so what is the shape of the curve, and how can you think of these shapes? Let me replace this picture here then by one that shows you the official way of thinking about these things, which and now what I show you here is a categorization of the what you were seeing before, namely the interface. So on the low temperature side, there's a liquid and there's a dilute vapor, and this essentially corresponds to this side of the phase diagram. On the phase diagram, which is pressure versus temperature, you see here at higher pressure the liquid, and on this red line here, it coexists with the gas. This particular point here is where we lost essentially the site of the interface, and this then is the critical temperature. So this is both the critical pressure and the critical temperature. And way above, or even very close above, there's nothing. Essentially, there's vapor of slightly varying density because it's all in a gravitational field. So this special point here is the point, the critical point, and it's this that I want to ask about, and I want to say, well, what's the definition, or what's the shape of this curve? And the reason is that if any of you are used to looking at a parabola, it'll turn out that the simple theories say this is a parabola. But it's not a parabola, and that's going to be one of the surprises. Okay, so let's have a look at the surprise that comes up. Give me a moment while I talk about this. But one of the things I want to discuss is then, how should I talk about the shape of a curve? Well, you all know, you all have some familiarity with this because you learn a lot about circles. Now again, you are going to have to accept my apology here because this is not exactly a circle. And none of these are circles. Take my assurance that as I've drawn them here, they are all circles. And in this amazing equipment here, that doesn't want to tell you it's a circle, I could rotate it and you would see that they sort of were circles. Now, what we know about a circle is that the circumference has some very special relation to the diameter. So here's the circumference measured around, and here's the diameter measured across. And the relationship between the two of them is not so trivial. And what is the relationship? Well, it's pi, and we know that pi is about 3.14. Some of you will know more than that, 3.14. I always remember the first 6 numbers, 159. And after, I used to remember more of that, 265, 358. And we know now that this goes on, so I'll write it here, 979, 323. Okay, and it keeps going. So the question is, all right, that keeps going. What more can I tell you about pi? Well, this it's the ancients already, and that's why we use a Greek letter. The ancients already knew that pi was pretty important, and they therefore had a lot to say on the matter. And one of the things they knew, and one of the things they proved, that it's about 3 1/7, but 3 1/7 is greater than pi. And on the other hand, you can say, well, what about 3 and 10/71? They knew that it was greater than this. So you can start pinning it down. And for all engineering purposes, it's been long well known that it's 3.414. If you look in the Bible, you'll see that for simplicity in reporting to the authorities, they approximated pi by 3. But the builders who built the temple in this case certainly knew that it wasn't exactly 3. So one of the things I'm going to talk to you about is a series of Greek letters which are going to raise up here. Let's see if we can bring them into sight. Yes, these are the so-called critical exponents. And these are going to answer the question that I raised with you, namely, how should one describe the shape of a curve at a point? And bear in mind that the point that I'm really interested in is the point here at the top, where I'm going to argue that this is rather flatter than you might have thought. And what's the story behind that, being so flat? Well, let's go on a little further and address this question of how you should talk about the shape at a point. So the simplest way of thinking about that, if I can bring this up and show it you there. So this is the question of how should we think about the shape of a point, the shape of a curve near a point. And if I plot y vertically and x horizontally, as all of you have been trained to do, for good traditional reasons, then if it's more or less linear at that point, and the point we're going to do is the origin, well, then that's simply x, y proportional to x. Now, I've done here a wiggle, which we're going to read as varies as. So y varies as x. On the other hand, if y varies as x squared, then I have a parabola, and it looks pretty much something like this. Okay. Now, that's the one alternative as a parabola. There's another alternative, which is actually a parabola on its side, which is a square root. And so that's the alternative. And what you see there is that if it varies this way with a power of a half, it comes in vertically. What about inverse powers? What about if it diverges at the origin? Well, the simplest divergent is that of a hyperbola, which looks pretty much like that. And that's y varying as 1 upon x. If it rises more steeply than that, then I've plotted here, y goes like 1 upon x squared. And so you're getting by now the idea that the number 0 or 1 in this case, so let me write in y goes as x to the 1. Okay, this number is telling you something, and it's telling you the shape of the curve. If it's a more spiky curve, and now we can perhaps remember the curves that I was showing you for helium, those were really much more spiky than this. And so here's the root. If y goes as x to the lambda, then x goes as y to the 1 upon lambda. And so we can look at the values of lambda of interest here. And this is the way in which I want you to think about these curves. So then we can come back and say, well, if I look back here, and let me come back, let's say, so the way we want to think about these things is through the shape of the curve and through the exponents. Now, here I want to tell you a theory which you'll forgive me saying the biblical theory. It was the biblical theory because when I was a student, this is the only theory that was around. It was also the theory that won van der Waals the first Nobel Prize in the Netherlands. And he was one of the early Nobel Prize winners. And at that stage, our president introduced us to the question of the language. At that stage, if you were Dutch, you could write your thesis in Dutch. And Maxwell, James Clerk Maxwell, the famous British theorist, decided that this was sufficiently important that he would learn Dutch. Nowadays, the Dutch theses are automatically written in English, except for some interesting questions which are written in the native language. Now, one of the questions is then, well, what should we expect? Well, it turns out that in the science of thermodynamics, which is the underlying science here, there's a master function, and I'm going to sketch here a master function, something like that. It comes down here, and I'm going to have it go up again. I'm going to have it go up a bit more smoothly than I've managed to draw it. And then the question is, this is a nice smooth curve. What values of this exponent that we should have, what values of lambda are going to come up to play in this diagram? Well, they're limited in view, and let me indicate perhaps in black. Anywhere here, it's essentially linear. And you can say, well, on the way down here, it's also linear. So basically, we either have curves that are going up or going down, but the exponent at any normal point is at 1, okay? And that's actually embodied in a little bit of mathematics, which some of you will know as Maclaurin's theorem. But there's a special point at the top of the hill here, okay, and let me sketch that in. That's a parabola. And so that seems to be a reasonable normal point. And now maybe it was a parabola going the other way, in which case it would look like that. But that's the number 2. What about 3? Well, if you look carefully down here, there has to be a point of inflection, and I'm going to draw the axes a little skew-whiff here. If I draw the axes at a point of inflection, then that gives you a cubic curve, and it looks like this. If I draw it the other way, it would look like this. And that seems to be it. For a smooth function, a normal function, those are the only choices. And those are the choices with which van der Waals came up. And if that's the situation, then we would expect this to be a parabola up here, okay? An inverted parabola, it's a maximum. But, as we'll see, this is not necessarily the situation. And if you press onwards, well, maybe there's a very flat curve that would be a 4th power, or if I draw it this way, like that. Excuse my drawing. And you get the idea that it seems that only simple integers, or maybe their inverses, should come into play. But is that really the situation? Well, if you look here at this curve that Guggenheim produced, he points out that there's a simple formula that he managed to fit. And he was a bit surprised that he could fit this. And here he essentially shaped the curve, and what he found out here was that this was 1/3. That's a bit surprising, because 3 is a number here, but it's not a number that's appropriate to a maximum, which should be either 2 or 4, or if you like, a half or a quarter. So the question is going to be, what is this number, and why did the simple theories, well, the simple theories were based on this picture here, okay, that why did they go wrong, and did they go wrong? Well, let me show you that some of the evidence. At this stage, you might say, well, isn't it about time we had a look at the real world? And the answer is yes, it is about time we look at the real world. And here's a look at the real world for carbon dioxide under the critical conditions. This was done by a man, a private gentleman who was just interested in Oslo, and he set up a lab in his experiment in his basement. And as you see, he now got a nice straight line. And of course, people love straight lines, but why did he get a straight line? Well, let me show you what he's plotting here. So this is the temperature plotted vertically, and at the top is the critical point. And then he used a trick that physicists often use. That is, he said, well, I would like a straight line to show you that we can all see it's a straight line. and here are my experimental points. And what did I plot? Well, I plotted the cube root. So he's verifying this idea of Guggenheim's that maybe there should be something simple, but not one of the standard exponents. So I remind you again that if it's a maximum, it should be either a half or maybe a quarter. But what the experimental evidence is that it's a third. Well, you may say maybe he's not so good. I'd like to show you this picture here. Let's see if we can get that in. More or less we can. Okay. More or less fits. Now, here you see some more straight lines. But these straight lines are on logarithmic plots. The screen is pretty big up there. But when I was shown these data by Balserini in Canada, it was more or less, he had plotted it out more or less on the size of the screen. So this is very good data. And as furthermore, you see it's for two different materials, xenon and sulfur hexafluoride, very, very different chemically. This is a neutral chemically, it won't do very much. Sulfur hexafluoride is an interesting compound. And as you see, these are very straight lines. But what you may not notice is that they're straight lines from here about 1 part in 100, here about 1 part in 1,000, here about 1 part in 10,000, here about 1 part in 100,000. And Balserini had the data going on. He doesn't bother to show it you because he knew that at that stage it was being rounded by gravitational effects. And of course he did his experiments on Earth, and that's in the field of the Earth's gravity. So clearly here the answer is close to 1/3. You can sort of see I put here the slope of a quarter. Now let me come back to the original picture that I showed you here. This was the picture of the gas liquid, and now I've reproduced at the bottom here, roughly speaking, the picture you saw from Guggenheim. But I've now introduced the temperature, little t. This is going to be T minus Tc. I'm always approaching the critical point and saying, well, what's the power that comes in at the critical point? This power is beta. And I'm going to say, well, it varies as, and so this is my squiggly symbol, varies as I come in closely. And the question is, what is this? Well, the simple biblical theories, the van der Waals theory said this was a half, and the evidence I've shown you on your right-hand side says, well, it's surely not a half. It's somewhere close to a third, and so let me say, well, it's not a half, it's about a third. If I measure the specific heat, I expect, even for carbon dioxide, or sulfur hexafluoride, or xenon, you can check me out on any of these, and I get this large spike. If I ask what the approximation said, what the van der Waals theory, it said, well, there was a jump. And there isn't a jump. It's a very sharp spike. So that's the first thing that underlies the theory of critical phenomena. Things are not what we expect, and they are, in fact, very different. And they're very different in many ways for other materials. So what I'd like to show you here is a ferromagnet, and I'm going to cover up the bottom just for the time being so as not to confuse you. And so here we see a ferromagnet, and there's a bit of a reflection for which I ask your forgiveness. And now a ferromagnet has the magnetic field and the temperature. It was already discovered by the physician of Queen Elizabeth I of England. Her physician was then a medical person but also a scientist. He discovered that if I had a magnet, it lost its magnetism above a certain temperature. And this is now often called the Curie temperature, sometimes remarked unkindly perhaps that Curie had the foresight to have his name begin with C. and therefore this is still the critical temperature, even though we can remember it in the case of a magnet, it should be a Curie temperature. If I plot the magnetization along this curve beneath the Curie temperature, then I find there is a spontaneous magnetization, and if I just reverse this, it can go in either way. It can point up or it can point down. And so again, I'm using little t here, there's again little beta, and I'm using this by analogy, but when I work it out, I find that beta is still about a third, even for a ferromagnet. So one of the things we learn is that there is some universality to the behavior around the critical point. And I'm going to talk about approximate models in which this is embodied. Let me talk about the antiferromagnetism, and let me bring that up so that you can see it here. In the case of an antiferromagnet, maybe I should show you first what happens in the case of a magnet. So here I have a magnetic material, and just to check out what I told you, that it was about a third. Okay, and so what you should be seeing by now is that this is coming down very steeply, and if it were a half, this would be the nice parabola. It's coming down more steeply, so you know at once that beta is less than a third. And in fact, this is work of Heller and Benedek, and if I show you on this right-hand side here, let me show you on the right-hand side. Well, I'll show it on the left-hand side here. So this is a magnetic material. Manganese is the magnetic ion there. Here again is a straight line. Well, so again, you know now, here's the temperature. The critical temperature is known pretty accurately here, about 1 part in 10 to the 5. And here is the vertical axis, and they've plotted the cube. So again, the answer is very close to a third. Now, I've cheated on you here, because this is a magnetic material, all right, but at the same time, it's an antiferromagnetic material. So I've set one set of spins that tend to point upwards, and the neighboring spins tend to point downwards. So I can talk about the spontaneous sublattice magnetization here, and if I talk about the sublattice magnetization, then this is again close to 1/3. That's what the experiments show you. And on the other hand, if I look here and say, well, what about superfluids? Remember again the specific heat with the 3 peaks I showed you was originally about a superfluid. Well, let's have a look at what superfluids should say. And the superfluids, here's an early experiment. The data that are off the line are the other guy's data. As you know, it's sometimes fashionable to show how much you've improved on their data, and the data close to the line here are the data of Clow and Reppe. As you see, this has been known for some time, but not greatly advertised. And if you ask what is the exponent here, well, there's some subtlety associated with that. So I put it down here. This is again about a third, close to a third. I put a bar on top of this because it turns out that's what's been measured here is the superfluid density, which is not quite the same as what you might say. It's not quite the analog of the magnetization. So there's a subtlety here that we well understand. Okay, well, I'd like to move on now to say, well, that's all very well, but let's talk a little bit more about some of the reality situations here. So I'd now like to switch gears, as it were. I've convinced you, I hope, that there are these somewhat magical numbers that we would like to understand. And so let me talk about this from a little bit different point of view. So I'd like to talk about reality versus theory. So this is now getting to saying, well, we've got a picture, we've got these exponents, they're well established, how could we understand them? Well, real theory is then we're going to be a question of analyzing and dissecting things. We're going to have to choose some sort of basic equations to understand it. And if we're only talking about as an engineer, well, the engineers are concerned with fluids and metals, so they certainly want to know what happens to carbon dioxide. They want to know about materials and fluids. The chemists are concerned with crystals, molecules, and atoms. If I come further down, the atomic physicists are concerned with electrons and nuclei, nuclear physicists with protons, neutrons, baryons, mesons, leptons. I may say, it may shock some of the members of the audience, that I got my first job on condition that I would teach nuclear physics. That's what it was about in those days. Then there are the particle physicists, and you'll hear from one of those, namely David Gross. And I may say that I would like to add to what was said about David Gross. He was not only director of the what is now the Kavli Institute in Santa Barbara, but he was also one of the outstanding directors, and it's now called the Kavli Institute because one of the things that David Gross did was to interest a rich gentleman living locally, Dr. Kavli, and that's why it's now called the Kavli Institute, and there are many other Kavli Institutes around. Then there come the grand unified theories, string theories, some of these things we've been hearing about. There are the basic laws, okay, the laws, Newton's laws, relativity. One of the questions that we quickly get into here is, well, here are the various theories, and these get further and further away from reality as it applies to engineers or chemists. Do we need to understand that? Well, not really, because, and let me put down here the issues beyond that. Forgive me a second, but I'm a little confused by where I want to be. And yeah, I want to be here, and I want to talk about something that seems to have disappeared. Okay, I've mislaid a transparency here. But what I wanted to talk about was the problems of approximation. And let me bring them up here. So we have the various theories, but then we have to understand how they can be controlled. We have to understand why Newton was so successful and why it was a few hundred years before Einstein was able to come along and say, well, that's not the end of the story. And in particular, if we have a controlled approximation, then there's no need, if we have relativity, if the velocities are much less than the speed of light. So we know that the speed of light is the crucial scale at which you have to worry about relativity. Similarly, in quantum mechanics, we have to know. The difficulty comes when we have uncontrolled approximations. And now the uncontrolled approximations come in pretty much whenever we have a complex system. And so I've indicated here some of the complex systems. And a heavy nucleus is such a one. Big atoms, large molecules, polymers. We, at the specialist conference this morning, we heard about polymers and the way in which they set themselves up to form proteins. Liquids, solid crystals, liquid crystals, glasses, plasmas, phase transitions, and critical phenomena. These are all situations where there are many variables, many scales, cooperativity and competition between different things that come into play. Can computers help? Well, if you want to ask questions, I think there may be questions at the end of the afternoon. The answer is not nearly as much as one would hope. They're important, but they don't help very much. And so I'll hold aside some answers to that question just in case they come up, but I don't think they're going to be of much interest to us. Basically, the computers don't help. What we do need is good mathematics, And one of the reasons we're here, those of us who are specialists in this area, is because Yang and Mills, many years ago, 60 years ago, introduced a beautiful bit of mathematics which is very important for understanding. But now what I want to talk about is very, very simple models. So I want to catch up on some of the things I was talking about before and talk about simple models. And what is the simplest model we can think about? The simplest model turns out to be something that was poo-pooed by professionals because they knew this wasn't the nature of life. Okay, wasn't the real nature. And this is where the question of intelligent approximation becomes crucial. So what I've put up on the left is a lattice, and I've indicated that if one wants the simplest possible model of a magnetic material, one knows that there are electrons, that they have spin, and they are spinning around, they're carrying a magnetic moment. The simplest picture is that the magnetic moment can either point up or point down. And so if it points up, well, it will point up like that. If it points down, it might point down here. There have to be some interactions around if I want something of that sort. And this is the simplest possible model of a magnet. It was poo-pooed because we know that that's an oversimplified model. But the question I'm going to address is, yes, it's certainly oversimplified. It's a gross approximation. But it turns out that if we can solve the mathematics, and it turns out that the mathematics is very similar to the dimer problem I showed you originally, the dimer game, how many ways can you fill a board with dimers? If I can solve that, then I can solve that problem, and I can solve this Ising model. Now it turns out that if I want to think of it in other terms, it's also a model of a lattice gas. Why? Because I can say, if there's an upspin, okay, if there's an upspin, that's right, but I can think of that as a vacant site. If there's a downspin, I can think of that as an occupied site. And if I imagine that the atoms, here I draw an atom, have some sort of repulsion, then I can't put two atoms on a given site. If I want to say, well, why do I have a ferromagnet? It's because there's some sort of interactions that are favorable between two spins that point the same way. And so these would also point the same way. And that means that here I had a downspin, so that means there should be some sort of interactions between atoms. So this is the simplest model, the simplest lattice gas. And this has been understood by chemists for some time as a very crude model. But then the question is going to be, can one deal with that? Can one solve this model? That's what I'd like to talk about next. And it turns out that, yes, indeed, you can solve this model. And if you do solve it, then you can find quite remarkable results. The man who solved this model was Lars Onsager. And here's what he found for the specific heat. Okay, and this should ring a bell with you, given that here it is, the specific heat of the two-dimensional Ising model, and I show it going through the ceiling here, okay? It's going through the ceiling, and that's because it diverges, literally. Now, it doesn't look so much like the pictures I showed you originally of superfluid helium, but here I'm pushing it up, and at the bottom, I'm showing you what formula Onsager established. This was a remarkable result and didn't have much impression at first. Although Wolfgang Pauli, the famous theorist who came over to the United States during World War II and spent about 5 years there during the war, he wrote back to colleagues who had been, owing to the war, unable to stay in touch with scientific developments, and said, look, you don't need to worry very much. The only interesting things that's really happened is that Onsager in 1944 solved this problem, and what he found was that there was a logarithmic divergence in the specific heat. So if I define little t again as the deviation from criticality, remember this is a model of a ferromagnet, but it's also a model of a lattice gas. This is it. And the logarithm of 0, as I hope I don't need to tell you, is essentially infinite. So this is the result. That's very striking. Now, the result goes on in other directions, and let me tell you some of the other pictures. The method that Onsager used to solve this is quite interesting, and over the years these methods of course get simplified, but I wanted to relate it to the dimer problem. And so if I could solve the dimer problem, and I can, on this peculiar board and with these shaped diamonds, so that here's a diamond which I want to weight with a number z, and here's a diamond with I want to weight with a number y. As you see, they point in different ways. And here is the relative weight. For the number z, I can just put in a 1, but for the number y, I want to put something that depends on the temperature. If I can solve this model on this slightly funny shaped lattice, then I can solve the Ising model. And so this is essentially the route that Onsager followed. And I'd like to tell you a little bit more about that. So let me put aside here, summarize what Onsager found. He found that it was a specific heat. There was this logarithm. It diverges, becomes infinite as I go to the critical point. But he did more than that. What he found was, and this is what I already suspected, I urged you to suspect, was that this wasn't just a special case. This was what you should expect more generally. So I'm going to hold this one aside, but what he showed in particular, he said, so, well, supposing you have a very asymmetric lattice, so a lattice in which the interactions in one way are much, much weaker than in the other way. So let's say I have the interactions here, and they're J prime, and they're 1/100th of the interactions along it. Well, the specific heat at first start looks much different. But then you see this logarithmic singularity. And here I've put the logarithmic singularity in the symmetric case. In the square lattice case, this is the one you would expect, but it's still the same logarithmic singularity. So this gives rise to a concept of universality. So we recognize these days that if you're looking at a special point, a singular point, and these points which don't obey the simple laws that I showed you before, these are called singular points. These singular points are very different. And now, one of the things that Onsager did, but he was a little reticent about publishing it, and so in 1979 and 1949, he mentioned this to a number of people. He even put it in a conference, but he left it to Chen-Ning Yang to do the hard work of actually publishing a paper, and the result was that beta for d equals 2, let me correct this, I want d equals 2 here. What was the value of beta? And the value of beta in this case was totally unexpected, 1/8. We don't understand 1/8 at all. To this day, we don't quite know why it's 1/8. It is 1/8, and there's no argument about it. So we'd like to understand that. The universality I mentioned that Onsager came up with. Let me show you some of the pictures here. Onsager also showed that the Ising model was the same on a rectangular lattice, on a triangular lattice, on a Kagome lattice. I used to think that Kagome was named after some famous Japanese gentleman, but no, it's just the Japanese word for a suitable lattice in which you can weave flat things to make a seat. Okay, so that's the Kagome lattice. It's a famous lattice, and it has these results. Well, this is all very well, but what about the real world? What is showing up in the real world? And so I'd like to move on to tell you some of what's actually showing up in the real world. Can we actually check on some of these specific heats, and what sort of results do we find? Well, generally, the question is, the specific heat is often close to singular. What sort of values should we expect? Well, let me make sure I get it right and don't want to mislead you. It's late in the day. What sort of values should we expect? Well, alpha is about not quite a logarithm. So early people thought that alpha was a logarithm, which would actually correspond to 0. But actually, alpha is better thought of as about a tenth, 0.09 and plus or minus 2 in the last place. Superfluid helium, I've already mentioned to you, and I'd like to show you some of the later data on that, because this is a beautiful material, and Leeper at Stanford was tempted to go on looking at it, and here is his latest results in 1996, and you see they go down to 1 part in 10 to the 10, 1 part in 10 to the 9, and you see again it's a strong slope. He reckoned it was very close to 0.0129. So maybe I can put that in here, 0, but slightly negative. Well, you can soon think about this. And yes, yeah, thank you. So minus 0.0129. For magnets, there's a different answer, and it's about 0.1. So let's say it's about 0.1 here. That's again minus. So there are a number of results here that one would like to know about. Okay, so the experiments are then interesting. One starts asking, well, what's the difference between argon and superfluid helium that our simple models left out? And there's an answer to that. And the answer to that is, well, one of the things the simple models left out is the effect of symmetry. And one of the beauties of the meeting we're at is that one of the things that Yang and Mills did together was point out some of the implications of symmetry. And well, in this simplest case, if the spin points either up or down, it's essentially a scalar. And so if it pointed continuously up or down, turns out that if it's a scalar, that's one of the results. That's the only thing you need to know, is that the spin would be a scalar. On the other hand, if the spin can point out in 2 directions and has a phase, then that's a sign of a quantum mechanical possibility, and superfluids and other quantum fluids then obey that situation and correspond to being planar. If, as in a real electron, it can point in any direction, in other words, the electron spins and has a magnetic moment, but that magnetic moment can point anywhere, then at least there anywhere means in 3 dimensions, and so we must look at the situation there. So we reach the conclusion that the exponents alpha for the specific heat and beta for the magnetization, or what's known as the order parameter, those are the crucial things. There's one other parameter here that I want to mention, and that determines the question of magnetization and dimension. So what's the question of dimension? Let me mention the question of dimension. Here is a picture that I'm rather fond of. I don't want to explain it greatly, This is what I call the plane of theory. And what it shows is vertically I'm plotting this variable n, this symmetry parameter. One can take n to infinity, and it was then shown that the model there is understandable. But along the bottom here, I'm noting the dimensionality. And the dimensionality is important. Of course, we live in 3 dimensions. The Onsager solution of the Ising model was just for 2 dimensions. If we lived in 4 dimensions, then van der Waals would deserve his prize fully, because the exponents he would predict would be correct. So one of the interesting things has been theorists have started thinking about dimensionality. And already this is then the picture that I want to show you. And I would like to say then, well, what's the situation in 2 dimensions? Can we look at symmetry in low dimensions? Can we look at 2 dimensions at all? Can we check on this result of Onsager and of Yang that in 2 dimensions the answer is going to be 1/8? And the answer is, well, if you're ingenious about it, you can do so. And so the question is, can you get 2 dimensions in the real world? Well, you have to have chemistry friends. And happily, I have some friends who are chemists, and they're very ingenious, because what you need is a magnetic material. But most magnetic materials come in nice crystals. They're 3-dimensional. But every now and then, you can put some compound in that's non-magnetic that separates the layers. And if you separate the layers enough, so here was the manganese fluoride, which is definitely 3-dimensional, and this is the slope, this is the magnetization, again on a log plot. And here, if you separate out the nickel, which is the magnetic ion, by layers of potassium fluoride, which is non-magnetic, then you can essentially get a 2 dimensions. And so here you see the slope, which is close to the 1/8. And now you can say, yes, but couldn't we go down further in 1 dimension? And the answer is yes, you can actually go down to 2 dimensions if you're prepared to look at a real 2-dimensional system. How do you look at a 2-dimensional system? Well, you choose another Chinese gentleman, someone I've known for many, many years. He was a graduate student at Cornell when I was there. That's Moses Chan. Moses, of course, is his adopted name. Huang Wei is his actual name, Chan Hang Wei. And working with a Korean student, he looked at a monolayer of methane on graphite, on the surface of graphite. Graphite is a beautiful material. If you split it, it can come in 2 dimensions. And by a very ingenious method, here he was able to verify. And instead of 1/8, which I remind you is 0.125, well, he said there's an uncertainty. He's an honest experimentalist. 0.127 was his optimal, but you see the uncertainty. It surely includes 20 in the last place. That surely includes 1/8. So one can, in fact, check on 2 dimensions. And that's the end of my story. Close to that. And so then you can ask, well, how about a formula for some of these exponents? And let me show you a formula. You would like a formula for the exponents. One of the ways of doing that is to say, well, we already noticed that they depend on the dimensionality and the symmetry. What can we do in terms of the dimensionality? Well, dimensionality is, from this one point of view, just a number. If I have a 1-dimensional system, well, the volume is just twice the diameter. If I have a circle, as we were looking at originally, it's pi times the diameter, but it goes as a power here. And this power should be volume as r squared. When it comes to a volume in 3 dimensions, I need the diameter cubed. When it comes to a volume in general dimensions, I need the volume to the d. Why not pretend that the diameter and the dimensionality is itself something that I can play with. And if you do that, then we can actually write down a formula. And the formula I'd like to show you, these were generated originally by a good colleague of mine at Cornell, Ken Wilson, and myself. And we said, well, let's start at 4 dimensions. I told you that 4 was special. So let's start at 4 and come down below it. And so here's the beginning of an expansion in epsilon for the 4 dimensions. And if you just truncate this expansion at the lowest order term, which is the quadratic term, then you already find that you get some sort of sense out of this. So for alpha, you get 0.08. Well, we reckoned it was about 1 for n equals 1. For superfluid helium, you get about minus 0.02, so you get it slightly negative. And for the magnetic materials, you get minus 0.01. So this formula works. When I write down epsilon squared plus dot, 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 that doesn't mean that we know all the answers. We don't know. It's been computed. It's very hard work to compute it beyond 4 dimensions. This is, in a way, the end of my story, because then the question is, yes, but what methods did you use to justify this sort of expansion? Well, that would take me too far afield and would take me furthermore into areas that are not really relevant unless one's interested professionally in understanding what's going on. So I would like to just close by showing you once more this very, very sharp behavior, and on this side showing it you broken down into separate sections. I'd just like to remind you that this is dysprosium aluminum garnet. It's a solid. So in the same way as I showed you originally superfluid helium and the alpha that describes that, here for dysprosium aluminum garnet is the same thing. And so this closes my circle. I hope I've given you some idea of the way in which one can think of these things. One has to go in stages. I've used a lot of pictures. Some of them have been pictures of experiments. Experiments underlie real science. Some of these pictures are then models. Well, it maybe works like this. And if it's a matter of biology, it becomes crucial to have models and to understand that they're approximate nature. And then there are questions of the approximations, and then there's the question of the mathematics. For the non-specialist, the mathematics can be left to the mathematicians, but that's often quite profound, and what has been learned is that approximate solutions to the mathematics are often very misleading. So on that note, I would once again like to say what a pleasure it is to be here to honor Professor Yang Chen-Ning, Frank Yang, and to say what a pleasure it is to have addressed this afternoon. Thank you very much.